Hey, Maria, good to see you here. Can we go over the interpretation of R squared value on assignment 7? I just wanted to make sure I'm wording it the correct way. That's awesome. Let's do it. Put up a little music right here, and we'll start looking over some assignment 7 R squared. So BAS 320, assignment 7, interpreting R squared. Which one? Let's look over here. Where's the R squared on here? Let's see here, R squared. Which one is this? Which one has the R squared? Oh, report the value of R squared. Here we go. Found some. The model, report the value of R squared, interprets number. Here it is right here. Okay, so let's talk about this value of R squared. So this is going to be 1D. So Q1D. Q1D. Who all is here? Who we got in the chat? David, good to see you here. 2E on 475 in the queue. Yeah, let's do one next here. Can you go over chapter quiz on the 3 different car repairs? Yep. Get Stat Tool 1, chapter 12, car repairs. Got that one. Can we do chapter 12? So the quiz is different numbers for me. Which one is that for you, Zach? Can you tell me which number that is? Because every number on your quiz will be different from mine. So which one is that, Zach? Hey, Abigail, good to see you here. Which one is it? And we'll do the 475 here coming up next. So which one is that? Not sure if you did 1C. I think we did 1C. We could do it here. I'll put it in the queue. BS 475, assignments 5. We got a few things in the queue. Assignment 5. Oh. And we got stuff in the queue. 1C. Okay, let's go do some R squared. A student figures there's a 1% chance of being late, and that's the miss the train question. Stat Tool 1, chapter 12, train question. Okay, we're good to go. We got 5 things in the queue. Let's get started here with some R squared interpretation for 320. Let's do it. Okay, so we're going to interpret some R squared right here. With interpreting R squared is the percent of variation Y. Oh, we can do dress chart too. You got it. R squared is the percent of variation Y explained by the variation X. So this instance, though, we have multiple X's. So I'm going to insert some data right here and talk through this a little bit here, but it's not going to be your data. So be careful. I'm not using your data. I'm going to insert a chunk, and I'm going to put the classic, not your data. So is this your data? No, this is not your data. Be very careful. I'm loading in different data. So don't do what Brian's doing right here. Don't do the exact same thing or you will get a wrong answer. Just want to make that very clear. This is not your data. Not your data. We're going to make a linear model right here, and we are going to try to explain people's weights from all the variables in this data frame. So the format y tilde x comma data equals is every single variable. Y tilde x, or y tilde dot, excuse me. The dot right here stands for all your variables. It is the x, meaning all the x's. So when I make this right here, you can see the linear model, when we summarize it, is going to show every single x variable, which is a lot of them. We were trying to explain, this is the y variable of interest, the weight of somebody. How much does someone weigh? And we use their gender, we use their height, we use their desired weight, their GPA, all these different variables right here were used. So the question becomes, what is R squared? Well, first off, can someone type in the chat, what is the value of R squared? Now, this is a good thing to see, especially if you're in 320. If I just say, what is R squared for this model? Like, what is R squared? What is the value of R squared? Can anyone see what the value of R squared is in this model? Be careful, because there's 2 values right here. So what is the value of R squared currently on the screen? Where is R squared and what is the value of it? So we first need to know, where is R squared right here? Where is the R squared? Where is R squared? What is it? Who knows? Take a moment right here. See if you can find it. Where is R squared? Does anyone see it in the output? To be like, where's the R squared in that output? So to get R squared, we need to run summary. Summary has the R squared inside of it. There's 2 values you might be between. So I always like to point out which one is R squared and where is R squared. So R squared is the multiple R squared. Multiple R squared is our value of R squared. So this is the value we're going to use. R squared is out of 100%. And it actually deals with how much of the variation are we explaining. So we could go down here and say, let's move the decimal. 81.14% of the variation in Y, now make sure to put in the values, 81.14% of the variation in y is explained by the x's in our model. Now, there's a lot of x's, so I wouldn't list them out, but I would simply just input the y right here of weight. There it is. So when we interpret r squared, it's the amount of variation in y explained by the variation in x. But there's another thing right here. So let's put another segment in the video right here. R squared adjusted. R squared adjusted, we're going to be doing another segment right here. The r squared adjusted is a little bit different. We'll do interpreting r squared adjusted. R squared adjusted is a much fairer look at the r squared. When we do r squared adjusted, it's actually a penalized r squared. So it's r squared with a penalty on it for how many variables we're putting in the model. So while r squared might go up, r squared adjusted could go down. And more importantly, and you'll see this in this example, if we have here a y variable, and then we have a bunch of x's, let's just do random normal x, and we'll just do 100 digits of that, and we'll do 3 x's. So these are just random variables right here, not associated with that y, and then we're going to make a model where we predict the y variable we just created, a random y variable, with the x's we have right here. And we'll just add them in because they're not in a data frame, and here's our model, didn't capitalize, and we're good. Now, what we might see is the concept that r squared adjusted can be negative. R squared adjusted is always lower than r squared. It's a penalized r squared for how many variables in the model. It's adjusted, more variables, more penalty. Now, if r squared's really high, we'll be fine because it's not going to get penalized a whole bunch. But when r squared is really low, you really see the penalty. And r squared adjusted can be negative. There is no interpretation to r squared adjusted. So let's write down some keynotes. 1, r squared adjusted. So adjusted r squared can be negative. As you see right here, it can be negative. 2, whoops, wrong thing right there. 1A on the first. Is that for 475, Carter? Is that for 475? Tell me which cost is for. Is it for 320? Trying to think which cost. R squared adjusted is always lower than r squared. 475. Yep. And we'll take a look at that here in a little bit. It's we'll put it on later, and we've done it earlier this week too. But we'll take a look. We'll put it on the list. It's always lower than r squared. There is one instance when it's not lower. The one instance when it's not lower is when we have an r squared of 1. I could probably replicate that by making such a small model here. And now it's telling us we can't even estimate them. I like that it says we can't estimate it right here. So when an r squared is 1, it's not letting me estimate it, but we can't even get estimates due to multicollinearity maybe. But this right here, there are instances, the one instance I should say, when you have an r squared of 1, that you will see the r squared adjusted is also 1 because it's penalized on what you were not able to explain. So 1, it's always lower than r squared. There's that one weird instance when r squared is 1. Ignore that. It's always lower than r squared. No interpretation of it. There is interpretation of r squared. R squared is the percent of variation y explained by the variation in x or the x's in the model, but there's no interpretation of r squared adjusted. So key things we should know about r squared adjusted, and it's a fair way. So we use it to compare models of different size because bigger models will get penalized more. So if a model has like 20 variables, we can compare it to a 5 variable model because they're each going to be adjusted for how many variables are in the model. So r squared adjusted, really great way to compare models. It's r squared that's been adjusted for the amount of variables in the model, hence adjusted r squared, and it's going to be lower than r squared unless, don't worry about that caveat, unless r squared is technically 1, there's no clean interpretation of it, and it can be negative as we see right here. It doesn't have to be negative, it's just for really, really bad models it will be negative. These are just random models right here with random x's, and sometimes it could be negative. Like if you see an r squared that's negative, you're like, that's horrible. That's absolutely horrible. Our model itself was not significant. Our r squared was bad. Our r squared adjusted is negative. That's horrible. No interpretation of it other than that's really bad. When is r squared adjusted good? That's the last good note to put on here. Closer to r squared it is, the better it is. Because you don't want to see them so far apart. We can use it to compare models. No worries, Carter. Yeah, we'll take a look in here in a little bit. Oh, we got the t-shirt question. I just get worried because we got a lot. Then I'm like, oh no, I got a t-shirt question. And we've got assignment 5. Q1A. Okay, let's go back. Next question. Okay, so we've got now 2E. So here we are with question 2E. This one. Hit 2 buttons. Okay. I think, did we do this one? Oh, did we do 1E? Oh, we did 1E earlier. So generate the forecast for the next year of data. Plot these along with the actual data from 2005. You need to filter just 2005. Comment on the forecast. Okay. So let's kind of do this with the, which are we using? The time series linear model. So let's go ahead and do a different time series linear model. Which data set are we using? We're using US gasoline, I think. US gasoline. So let's do a different data set. Okay, let's do 2E right here and talk about how to do forecasts. And let's take a look. Here we go. So this is doing forecasts for time series regression. So we have here generate forecast for the next year of data and plot these along with the actual data. So we're going to take some OS production data, and there it is right here. And we want to generate the forecast for this. But first we need a model. What kind of models did we use again? There's the test for that, Select the appropriate number of Fourier terms. Okay, so we're using Fourier, of course. And so we want to do harmonic regression right here. And let's take a look. We need to take our data, pipe it into the model, and it should be Fourier. No. Do we not have FP33 loaded up? It is loaded up. Let me get the Fourier. I always forget sometimes a little bit of the code. Oh, there's the book. And we go right here. There it is. Nope. There we go. Time series models. And here we are. And there it is right here. Boom. You have to do it in time series linear model. Boom. Okay, so let's take and drop it into the model right there. Time series linear model, it's straight from the book actually, because we're doing the beer one. Yes, same sort of model. We can do tobacco instead. And we're adding in the trend right here, the Fourier term. So actually, there's a question, I think Shiv was asking about it, but the degrees of freedom right here are going to actually be 3. We have 3 terms in the model. We have a trend term, we have a Fourier term. We could see this in the report of the model. Let's go ahead and run this through. It is creating the model. Let's go ahead and look at the report of the model. Here's the report. We do have 4 terms in the model. 1, 2, 3, 4. There we go. So we have 4 terms in the model right there. The intercept right there, not counting. We have 4 model terms for estimates of parameters in the model. And so when if we did a Legendre box test, we would add in degrees of freedom equal to 4 for this. Does look to be a pretty good model right here, but taking this right here and making predictions forward into the future, we need to use the forecast function. Off by 1 key right there. So forecast, this is only quarterly data. So there's the forecast for the next quarters into the future. Now this code, it took some practice. I used to have to look at the book for this one, but it's really nice what we can do right here. If we call this the forecast, so we're gonna, actually usually FC is better, just abbreviation right there, the forecast of the data. What we can do is we can take the forecast. Gonna get it right? Ready? I always make a little error. Yeah, what you do is you take the forecast. This is where the error occurs. Watch this. We're only going to see right now just this portion of the data right here. We're only going to see the blue interval. We're only going to see a very small blue interval. You ready? There's the very small blue interval. But you have to then take the original data set, and it's smart enough to know to plot with it. Ooh, what is going on? Because we need to remove out those other rows, I think. The data set does go into the future, so actually this is pretty interesting. We saw this in class today too. I think tobacco doesn't go into the future. Good to see you here, Matt. Tobacco ends at a certain point. We've got the check data from way previous in class. Tobacco data, I think, ends back here. And so the model, if you notice right here, has 2004 data, and then it's predicting out here. So what we want to do is we want to first filter. And let's go to filter is.na is not .NA, and let's put in here the tobacco. I think that should work. So is not missing of tobacco. That looks to be good. And now let's take a look at it. There we go. Ooh, what's going on with that model? The model's pretty interesting, and we are getting tobacco right there. We are getting the predictions. Does it really jump that much? That is an interesting model. So the model makes predictions that are that high. I don't know if I like this model right now, but here we are with our predictions for our model, and I'm not liking it. We could add another filter in and filter previous years, but this is using just the trend and the Fourier terms. Fourier terms. Because yeah, 2 free periods is quarterly data. We can only go up to 2 on it. It looks like. Let me do 1 harmonic term on it, and yeah. We would see the wave going through it. Let's extend it further just to see the wave better. Let's go to 40 periods going forward in the future. And that's what it's telling me it is. Well, that's interesting. I'm wondering why it's starting the series right there. I would have thought the series would be down here. So I'm a little bit concerned. Well, it's picking up on the... that's interesting. Not a good model so far, I think. So not too happy with those predictions. And want to make sure everything's going correctly right here. But this has got it. I think it was, who's asking about this? I think, was it Abigail or David was asking about it? What you're looking for is a model like this right here. This is not the exact model, but we could do this from many, many different data sets. We do have some other daily data. Let me do one more example right here. Just practicing making the models. This is the goal right here, is just to make models and to analyze models and see how they're doing. So let's see right here. Using 24 rows, all that good stuff. Let's take a look at another data set. Like, let's go to U.S. arrivals. Is that one? U.S. arrivals. Employment. Ooh, fun stuff right here. Employment. So here we are with the monthly employment. Good stuff. And it's for different sectors. So we need to go to select. And let's select only this right here. And we're going to go to filter, excuse me. Filter from this, just title equals this. And that should be in quotes. And there it is right there. We just have that one series. And let's go here to US private. And there's the US private data. Let's see if it's looking good. We're going to take it and auto plot it in to here. And there we go. That has a very strong trend. And it might have some sort of harmonic thing going on, but the trend harmonic might actually work really well for this. We're basically just using the same thing, but we don't need the filter right here. So it's a very similar code for this, because we're just going to take the U.S. employment, pipe it through to here, and then we're going to take in, and instead of doing the tobacco, we're going to do the employed instead, and we'll put a harmonic term of 2 to start, and just take a look at what's going on right here. And we're not doing loss production. That's going to be interesting if it plots. I think it's mad. Let's go right here and actually plot with this and see what we get. Oh, interesting. Taking a second. Always like when the plots take a moment to load. But it's loading in, getting the forecast right there. 71. What? What is going on? What have we done? So let's take a look right here. Did the forecast actually go through? So we have right here the forecast. Ooh, what's going on with my forecast? 59,000. Something is odd about this. Something is very odd. So let's see. My file is not in. If you could hop on. Yeah, definitely message me. Some sort of crash outside. Mine is being very odd too right here. What have I created? Did I even run that? It is running. My computer is being very odd. Oh my God. Oh, here's the plot. Oh, because it's got different series inside of it. Oh, ooh. Okay, let's delete all this out. These are different series. And so this data right now, the U.S. employment, ooh, it's being very angry. The U.S. employment right now has multiple series inside of it, and so we just made a ton of different models. So it's got like 5,000 models inside of it. So it's like maybe different sectors or something. Okay, now it's working better. So it's got the series right here, and we need to probably grab also a filter on the series. Let's go ahead and filter the series ID. There it is. Equals this right here. And let's take a look at this. Oh, it's mad about something. Oh, I didn't close the parentheses. Exit out of that code. And now let's take a look at this. Okay. Now I think we're much better because now we have only one series and it's loading quicker. And there it is, the employment rate of this group right here. So now we have our US private right here. And now, oh, and I think did we run the wrong thing right there? Oh, I did it on the full series anyways. That's why. Foolish me. And now we get what we want to see. Now we've got something much better. And now we have our Fourier model, our harmonic regression right here. We'll extend it out further so we can just see a little bit nicer of that. It's going to look a little ridiculous right here, but you can see the harmonic regression a lot better right here with the kind of oscillating sound on it. It is doing a bit of a step right there, which is interesting. We could increase the harmonic term on this right here to go to like 8, and we'll get more oscillations. It's mad because the series doesn't allow for that because it doesn't have enough estimates for it. But now we get more of an oscillating series, which probably looks pretty good. It's interesting it does that step. It's predicting a step right there downward in the series, but maybe 4 is good. I don't know. We could fit multiple models right here. Look at the AICs of that. And let's look at that last thing real quick, then we'll head back. But this should hopefully cover a lot of what we're doing because what you want to do with this is you want to make multiple models. You want to make an F4 model. You want to make, there we go, an F. Let's copy this. Oh. It's this easy to make all your models to look at. There we go. And then let's change these. We need to put in some commas next. And a lot of coding is copy pasting. Wrong spot for that comma. There we go. Oh my gosh. And I think that should be good. So let's take a look. Actually, let's take a look at without the forecast. And let's go here to the glance of them. It should run. There we go. So now the question becomes, which of these do we use? And we're missing some of our rows right here. Which of these would we use and why? Seems kind of, yeah, they're all kind of okay-ish. But the answer for which we use and why is going to be based on the AIC. The lower the AIC, the better. And it's kind of interesting that we should probably just be fitting one of those harmonic terms. The upper harmonic terms are increasing the AIC. This is actually like R-squared adjusted. We just talked about there with a penalty term. So, oh, and there's the degrees of freedom. So we should maybe grab that. I don't know why he doesn't just grab that, but those are the degrees of freedom. And I think we said there was 4 for one of the ones we used earlier. So those are the degrees of freedom being used by the model. So let's go back to our harmonic of one term and just go back down to this right here and take a look. How would we choose between the F1 and the S2? So this right here, probably F1 because it's simpler. Good question, Abigail, right there. I'd probably choose F1 because it's simpler in terms of, and thank you so much, Abigail, for following along. I like to do different examples, especially to like show different data sets, because it's not just about solving this one problem. It's understanding like, what are we doing? So hopefully these are giving the tools and techniques to solve other problems, because now we've created the model with one Fourier term in it, and we can look right here what's going on with it. So this should run. Everything runs. It has a great AIC. We can use the one with the smallest and most least Fourier terms. And then we could actually go in here and let's look at the GST time series residuals. There we go. And we should be able to get these out of it. So let's take a look at what's going on with these. No. No, no, no. No, no, no. Not good, not good. And we should definitely probably do this. Let me try this. Let me see if it'll let me just throw in this. Will it let me? No, it doesn't like that. We probably need to do that before. We need to difference it or something. Yeah, we need to do some differencing. I could difference it outside of it. Let me go to US private. It gets mad when you... So I probably need to mutate it. We'll try one last thing right here. Mutate. And so you want to use dplyr functions when doing dplyr stuff. And let's say diff employed. Diff employed is going to be equal to the difference of employed. And it's mad. Oh, because it's not the same size. And so when you're taking the difference, you'll be missing the first one. So we probably, could we add to it a concatenate? of a first element of it. Let me see. U.S. private employed and we wouldn't have the last, excuse me. So we would get right here, because the difference is going to be, just double checking. Yeah. So there is no value for the first one. So we'd want to concatenate onto it. I'm wondering if it'll let me do this. It's going to let me do it with the missingness too. Concatenate onto this. It's going to give me the same error. Cool. And let's concatenate a vector of missingness with the following. There we go. It got it. So the first one is missing, and then that's the difference, the increase. There we go. Okay, so let's rewrite this into itself. And we still have a Tisbel, which is very important. And there we go. Is it going to like predicting on the difference? Let's find out the hard way. It says to me it rans. Okay, it's fine. Ooh. Better. But now we see what? Now that we've removed the trend. So Abigail, this is the real deal right here. Yeah, the mutate can take a moment. So now, Abigail, what do we see right here? Is we see a what? Okay. Very clear. Is because very clear thing going on right here. That's the next thing we got to get worked on, which we might stop here because we're venturing into even more topics, but we're just kind of going through the lots of statistical significance and where is it at, and then look at that right there. It's kind of, I wouldn't say it's really an outlier issue. I mean, they are outliers, but it's kind of that there are, when you have that many outliers, it's less of an outlier issue. It's more of a pattern. So what's going on with this right here? Like, this right here is a big thing, especially those numbers are super important related to that. So there's definitely something going on right here that we would need to look at, because we've fixed it a little bit. We went from this, like this is ridiculous. We actually mentioned this in class today. This is ridiculous. So we went from this to this. So now we're on to this. So now what's the issue? And this is where we'll be going with kind of the end of the semester. So we went from a very strong trend in the data to now we've gone to this. So where are we at with this now? So now the issue looks to be that there's significant lag or autocorrelation on lag 6 and significant autocorrelation on lag 12. I can't remember what SS means on the ACF. There's statistical significance on it. So, no worries. That right here, if it's outside these blue lines, Abigail, thank you for asking. If it's outside these blue lines, it's statistically significant. So this right here means there's statistically significant lag at lag 6 and lag 12, which means last year's, we're predicting U.S. employment. Last year's employment is highly correlated to last year's time, last month. Like, this year's December is highly correlated with last year's December's employment in the U.S. This year's December is highly correlated to 6 months previous also, and rather the 6 denotes that, but if you think of it as like 12 and 6. But it's every 12 months, there's a very high positive correlation. Like, if there's high employment this December, there's high employment next December. Where if there's high employment this December, there's also high employment in the summer. There's some negative autocorrelation on like a 3 months difference, but the biggest things to catch right here are the 12 and 6 month annual and biannual patterns right there. So there is some extreme correlation right here. And in truth, we probably need to run an ARIMA on this, which, you know what, let's just finish it off. Let's see if it actually comes out really good right here. So we finished class with this, but the ARIMA model is really probably one of the biggest things we need to talk about in the class. Like, we're going to get to it, I think, not next week, but the week after. So the seasonal ARIMA is probably what we want. I just like using proper models. So let's go to the seasonal ARIMA, just grab the code. I always make sure I use the code some, but then it's like you forget right here, the auto ARIMA, which is the end all be all of ARIMA searches. So we're just going to take and put in our auto ARIMA right here instead. So let's call auto ARIMA. We're going to do it on the difference. Actually, AutoRima does differencing for us, so let's not even use the differencing. It has the ability to difference the data for us. And we're just going to take and we're missing a parentheses. Where's our, the model. And we'll put that there for the model. And we are doing employed, right? I think we're good. Data is missing with no default. Oh. There we go. Good. So now that we're using the AutoRima, it's actually going to do the differencing for us to try to figure out if we need differencing. And let's see how the residuals look for this. Hopefully they look better. And this is the goal. The goal is to make a good looking model and no good residuals when you see them. We saw a trend to start. We saw now we see some sort of high autocorrelation pattern. The other one did have high autocorrelation pattern too. This is taking a moment because it's AutoArima, but this is where we're trying to go to in the class. This is the goal. It's not about solving one problem. It's about working with the models until you find something that works, and then we would have evidence it works. I won't do the next step from here, but I would start cross-validating this model if I had it, because the question is this a good model? Does this make good predictions? Do we have confidence in this model? Should I use this model? And so maybe how's my CPU doing? I'm using 3% of my CPU. What just happened? Only 3% is being used right now. So we'll see if this works. We'll give it 1 minute to go right here. But Abigail, do you have any questions? Has this helped out, Abigail? Does this make a little bit more sense? And this is why we don't go to AutoArima first sometimes. Maybe there's easier techniques. AutoArima is not a very quick thing. It's actually doing a search procedure right now where it's searching through all the different models for me, trying to find the best possible model and seeing, awesome, I'm glad this helps out. But I'm doing a search grid right now. Where's the search grid he talks about? Estimating an OR selection. I am doing a big search right now, trying to find the best model. Like I'm looking here and then saying, well, let me go here, looking around it, going here. And it's just creating tons and tons and tons and tons and tons and tons and tons of models. And so it's still running. Very good computer right here. Just going crazy trying to find the answer. And it might find something good. It might find something bad. We'll check back in on it. I'm interested to see if the residuals look better because this is bad residuals. I think I need to rewatch them at Tuesday's lecture too. All of the models is getting confusing me. Good review. Make sure to understand what a Fourier model is. Make sure to understand the trend, the mean, the naive, the drift. There's a lot of different types of models. And we haven't even talked about ARIMA, so this is something we haven't gotten into yet. But we'll check back in on the model. We're going to head over to the next question. Car repairs question. Let me go back over here to 201. Can we still load up my Pearson? Hey, we didn't get the access denied, so let's load up some car repairs. Okay, so we're going to do the car repairs question now. Car repairs at 35. I'm assuming this is the 2-car repairs. Let's do the 2-car repair question. Here we go. Okay, so with the 2-car repair question, we need to take... There we go. The same question. We have a different version, maybe. We need to figure out the probability of a certain amount of repairs happening to our car. So let's go right here and start to figure out these probabilities. Now, if you get a question like this, especially on the test, start by drawing it out. Don't just try to juggle all the numbers in your head. I was trying to solve a problem earlier, and I was just like, I'll just run it in my head. And then I wrote it down, and it was so much easier. It was some sort of like tip problem thing. Do I still have that open from today? Maybe I closed it out. My mom sent it to me, and once I wrote it down, I was like, well, the answer's obvious. And I sent it to her in a picture. And she was like, oh, that makes sense. It was some sort of probably social media thing. So we go right here. This probably posted on Facebook. The probability of an event, and the event is what happened. Like your car got 0 repairs, 1 repair, 2 repairs, or 3 or more. So the E stands for the event. Like you could really write a table just when UT plays a football game, we win, lose, or tie, and then the probability of said event. So just understanding this notation is important right here. I'm just writing down here's the things that could happen on the left side, and then there's the said probability. Now, the probability of all these things needs to add up to 1 because it's everything that could occur. This is known as the sample space, not the sample frame. The sample space is everything that could occur. So the probability, as it says right here, of 1 repair is 16%. Doop. And the probability of 2 repairs is next, 7%. And the probability of 3 repairs is 1%. Now, the important thing to know right here is it doesn't give you the probability of 0 repairs because it expects you to use one of our rules of probabilities that states the sum of the sample space, all of these have to add to 1. So let's start adding up right here. As we add them up, they add to 24%. Well, then we can take and subtract from 1 and get the remaining probability. That it has to be that your car would get zero repairs 76% of the time, because this is just 1 minus the probability. We could also re-express this table now. And what do I mean by re-express? Just write it a different way, like the event of your car getting a repair and the event of your car not getting a repair. So getting a repair would be the following. There's your car getting a repair. So we would take those probabilities, put them here. And here is not repair, and we put that right there. So this is going to help us with the problem. I've done it a few times, so I know a few steps that help. If we just write it this way. Because it asks, first off, what is the probability your car, neither of your two cars will need repairs? So it's not just one car we're talking about anymore. We're saying we have two cars. And with these two cars, car number 1 did not need repairs, and car number 2 did not need repairs. So we had neither car needed repairs. Now, you have to hear the words very carefully on this when we talk about it. My first car did not need repairs, and my second car did not need repairs. First car did not need repairs, and second car did not need repairs. And please write this down. Whenever we multiply probabilities, we have to have that the two probabilities are independent of each other. So if I say my first car did not need repairs and my second car did not need repairs, the key word there, and, means we multiply them. And to multiply, we have to say, are these two probabilities independent? We'll assume it for this problem because it asks us to. We're saying the first car needing repairs would not depend on the second car needing repairs and vice versa. So it's like if this car needed repairs, the other car would not need, like, it wouldn't change the probability. The best example of independence would be like, I drank coffee this morning. Did that influence you to drink coffee? No. You drinking coffee this morning, if you did or did not, would be independent of Brian drinking coffee. I do have so many students who outthink the problems. They go, what if I see you drinking coffee, though? That might influence me. I go, darn it. Okay, then I say, Brian drinking coffee and Tom Brady drinking coffee. Tom Brady drinking coffee is independent of Brian drinking coffee. If I drink coffee this morning, it will no way influence Tom Brady to drink coffee, so his drinking coffee is independent of me drinking coffee. We could multiply that to find out the probability Brian drinks coffee and Tom Brady drinks coffee. So we're going to multiply these probabilities right here and do 0.76 times 0.76, and that is the answer to question A, or question 1. That's A, that's what it was. Now the next one asks, what is the probability that neither car will need repair? Well, this is a similar type problem where it asks the first car needs repairs, and the second car needs repairs. Once again, the condition to assume here is that they're independent, and I'm color coding it to help out with, we're going to multiply the probabilities of needs repairs, which is the sum of those probabilities, which is 24%. So the answer to B is going to be the first needed repairs and the second needed repairs. And so that will be the answer to B, and we'll solve it here in a moment, but we can just write it down mathematically and solve it in a moment. The last answer for question C is the complicated one. It's that at least one car needs repairs. So what is the probability for neither is correct? Great job, Cassie, right there. That is the answer. And the last one's the really tough one because it says, what's the probability of at least one repair? So here's what could happen. And let's write another sample space. You're like, sample space again? No! Well, this is what could happen with your two cars. With your two cars, it could be the case that neither need repairs, the first, the second, or both. So this is everything that could occur right now. One of these combinations of things must occur. Does that make sense, Cassie, for the last one? The last one's the tough one. Like, it is either the case that both your cars did not need repairs, the second one needed repairs, the first one needed repairs, or both your cars needed repairs. Like that, it is the case that this would occur. That neither of your cars needed repairs this year, the second car needed repairs this year, or the first one, or the fourth one. Notice how I'm saying or, because you could add these probabilities, right? It's just like the sample space up there where you could just add them to figure out the probability of 1, 2, or 3 plus repairs and do that. We're going to do the same thing again right here, but we already know one of the probabilities. We already know this probability right here is the following. That is the same thing we just found, the probability of both your cars not needing repairs. The probability of both of your cars not needing repairs is 0.5776. So that's the probability both your cars do not need repairs. Now the question asks, what's the probability at least one of your car needs repairs? Which would be that car, that's at least one down there. So Cassidy, how could we figure out this sum of probabilities? So we want to figure out all the probabilities right here. It doesn't matter about just a singular one, but how could we figure out the sum of all those probabilities? Because this is a proper probability table. Like we've mapped this out properly, and we know this is 57 point. Kind of, you're right. We want to know what the amount of all those are. So how could we figure this out? Because this table, we know what it has to add up to. You're on the right track. This is the sum of all those. Like, that's what that question mark is. It would be all those probabilities added up. So you got this. How can we figure it out? So think about how the probability table works and what would this value be? Cassie, 100 points. You got it. Yep. Because that's everything but your car needed, no cars needed repairs. So at least one car needing repair is everything but none of your cars needing repairs. So you could subtract from one and you could get the remaining probability. So that's exactly it. Great job. Let's go back to the question. That's not the answer. Next one is 24. So this one really is 1 minus, and there's that. And this one is 24. And definitely check out the question as we work through those. As long as we carried all our decimals, you're welcome. Great question. That's a fun one. It's a good one. Good practice right there. And make sure to know your rules of probability. We can add together all those probabilities because they are disjoint. So the reason you can add these is because they can't all happen at the same time. You can sum up these like 7 and 1% because they're disjoint. There's no overlap. There's no case where your car gets 2 repairs and gets 3+ repairs. So you can add probabilities that are disjoint. You can multiply probabilities that are independent, and make sure to review the terms independent, disjoint, know the multiplication rule, know the addition rule. Good practice. Back here to the main screen. Okay, working away right here. Next problem is assignment 1C for 475. Let's take a look. 1C. One C is the intervals. We have some of it supplied right here. Okay, let's take a look. I think we've done a good bit of this one, so let's go ahead and take a look at this. Does it want us to auto plot it? Auto plot the original series, add an auto layer to show the forecast. Yep. Book has really good stuff on this. So let's go take a look at it. Here we go, checking it out. Let's take a look. What does it say? I tried to look in office hours, but I wasn't sure. Which one? Which one were you looking at? Let's take a timestamp right here. 44:52. Which one are you asking about again, Abigail? Let me know. Is it this one right here? So what we need to do is this is the data right here. 1C, awesome. Let's do it right now. Let's check it out. We'll probably just do this one fully. I think we did fully in another one, but what we need to do right here is we need to create these new scenarios. So these are the scenarios right here. The electric data is not found, so we need to go ahead and create this. Do I have it created in here right now? Nope. This is the interpretation thing, the explained Hilo, that he's so good at code. Like, even I'm like, okay, I gotta make sure I just, such good code. And so now we're gonna go ahead and create this. It's not the augment, see, that's what gets me. It's the summarize. So we're going to create the January data right here. Let's go ahead and create the January data again. Good practice. Okay, here we go. Half-hourly data from the Victoria Electric data. So important to know what you're working with. Always look at your data. Does it make sense, Abigail? What we have right here, we have half-hour data collected every half hour on the demand and the temperature in Victorian Australia, on just our electricity demand and temperature and whether or not it was a holiday. And you can just see all the data right here for everything. If you go and look further, you can just look at more data and the date right there. So this is starting in 2012. So the first thing it says is extract the 2014 data, extract only January 2014. So we need to go ahead and do filter. And let's go to filter. And we want to do year month, I believe it is. Year month on time. And equals to we should say, will Jan 2014 work? It's mad. It's always mad. Oh, I think we have to do as date. It's a specific as date. No, we don't want to do a base as date. There's as date with Lubridate. I think will it accept Lubridate? It might. It might. There's things it likes. There's things it doesn't like. It doesn't like it. Doesn't like the equals equals. Doesn't like the equals. 2 seconds right here. Always got to double check the book. Can you give her 1G? Yeah, John, let's take a look at that here. Just a moment, you bet. So let's take a look at 1G. Be coming up here in just a little bit. BS 320. Assignment 7. Assignment 7. 1G. That's 1G right there. And so year month on time. That should take out the year month. Okay, let me make sure it's liking that. And let's see if it's working on it. Always do your code in little bits. Okay, it is working. And so now it's mad about this. Let me go to the book. Always check your code with the book. And we're just going to double check our running of it. And there's the year month. We got a filter. And filter year time. Oh, yeah, there's the year. Do year month. Really? Oh, it's not on there. Year quarter greater than equal to. He's just doing yearly data. I thought it'd like it. It should be happy with it. Yeah, that's probably the format. The format. Oh, Abigail, I think you're right. Well, look at this right here, Abigail, 100 points. The issue, and I should have just looked at the code. The issue right here is it needs to look like this. Let's change. Is it going like that? Doesn't like that, but I think it should be happy now. It's still mad. Still mad. Always mad. No, it should be equals equals. So close. Sometimes your brain just overheats. Filter should have greater than equal to, so it should be equals equals. So we should be able to say year. Let's make sure it's just working with the year. There's Lubridate. And okay, that's fine. Oh, there it is right there. Oh, I got to throw it in a year month too. So easy to make mistakes on it. It's not registering that as a date. Oh, what's going on? What do we have? Oh, wait. There we go. Thank you, Abigail. 100 points. Easy to make errors right there. And let's go to summarize. And with the summarize right here, let's go ahead and take, like it says aggregate right there. Let's go ahead and take the demand and get the daily demand and do the sum. Let's go here and say demand equals to sum of demand. And it is demands right now. It's demand. I think it's just demand. And there we go. There's the sum. We need to re-index it, right? Need to re-index it. Let me double check. You want to filter, index, and then summarize. Index by, yeah. So we need to filter, index, and then summarize. So index by. This one is one I always get wrong. Index by. Because now we need to index by this. Index by. I might even look in the book real quick. There we go. Index by year, month, year. So we need to grab this. And so many codes to remember. Index by, and we want to go the date or the time is equal to year day, it should be. Or no, we should be able to just do, I think, does it just do it? Because now we index by, I think we should. As date, yep. That's the He mentions that too as date. Thank you, Abigail. My brain is overheated today. That should be fine on this now. Nope. Everything is getting the table working. It is mad about everything. Index by date equals. Wait, is it not? Is it date? Oh, because it's mad about that. There we go. And there we go. There's the date. Something seems a little bit off about this, though. And then we can summarize. There we go. Got 1A from... I know. I'm working on 1A right now, and it's... Abigail's helping along. Abigail, 500 points. I did it during a different office hours, and then my brain's just thinking, like, it is fun getting it to work. Now we get to the summarize portion. Now let's go to the summarize right here. Let's add in the extra one right here and go to... you can go to temperature. It's going to overwrite it if you do this, though. Max, temperature, autocomplete is our best friend, and there we go. This is the easy part. I thought this was 1C. No, well, we're doing 1C. We gotta do 1A to get to 1C. So sometimes your brain just overheats. You're like, oh man, later in the day, been coding a bit. So I think we've done it now. Let's go ahead and store on the outside of this over here to the January daily electric data. There we go. Data's been stored. Got it reindexed. Got it daily demand. Yeah, no, it's good practice. That's why I like doing it a few times. It's just so easy to make mistakes with the code. It's just practice, practice, practice. Even I like to practice. And so 1C is a little bit easier now that we have this. So let's go down here to 1C, and we can actually make the forecast with this. So we need to take this data right here and make our fit right here. So if you notice, we need the fit for the model. So we're basically having to do all of it. So produce a residual plot. We don't have that yet. Plot the data with regression. So now we need to make the time series model right here. We're kind of just doing all of it. So here's the data. Data's right there. Let's go here, pipe it into a model. And the model is going to be the time series linear model. Let's call it, sure, we'll call it TSLM equals to, say time series. There we go. And then TSLM. And now we need to take we're predicting demand and we're doing temperature. I do want to say this, whenever you make stuff, please take a look at it. I think that's one thing people forget is that the whole point of this is not to do steps. Whenever you're at a job, no one's going to say like, do this step, do this step, do this step. We need to know, why would we look at a report? Why would we look at a glance? Does this make sense to everybody right here? Like we were doing this a second ago. I'm a little more focused on this question. But why would we look at report? Report is to look at the coefficients of the model. Why would we look at glance? We want here to look at the AIC mostly, which is off the screen, I believe. But we'd want to look at the AIC of the model to see how our model's doing. Unless it asks, you don't have to do it unless the question asks, but you know, like those are things we should consider. And then last but not least, we'd probably want to look at the augment too, which is going to give the predictions. So understanding what things are like report, augment, glance, these codes right here are very important to know. Like, why would we need the augment, which actually we can, and I think we will be using in a second to do the plot of it. I think this question asks it, or it's asking us to plot the predictions on top of a model. So here we are with the fitted values from it. So let's go ahead and take, and this will be our model. So just understanding what we've created a regression model of sorts, a time series linear model, and I called it fit, good. And then down here, we've got the next day scenarios, and then we've got the fit. Now we are going to take, and we're going to forecast the new data onto the next day data. And so we are getting the forecast right here. These are the hot day, cold day scenarios. For 1B, is there a separate fit that we need to use to produce the output, or can we just use it from 1A? I'd have to take a look. 1B says to produce a residual plot of the TS residuals. Is this model accurate? Are there any outliers? I'm pretty sure it's from that model, correct? Plot the data, find the... Is there any way, is there a positive relationship? Why is there a positive relationship? Positive relationship is denoted by the following. Why is there a positive relationship? Was I getting the wrong model earlier? Why is there a positive relationship right here? Why is there a positive relationship? Why is there a positive relationship? So why is there a positive relationship right here? Kind of. The coefficient is positive. It is statistically significant. It is positive. The coefficient is positive. And kind of, yes. And you can see it also if you plot it. But also the coefficient's positive, things like that. But the model shows a positive relationship. So that definitely shows up. And what you'd want to do right here is if you want to plot it, you'd need to go right here. You'd want to forecast. And it should allow us to do a forecast horizon. There we go. Oh man. Forecast, column, time series model, temperature not found. This is why we have to do the new scenarios. Exactly. So we have to do the new scenarios to do the forecasting right here. We could look at the residuals of it. So fit GG time series residuals. And here's the residuals of it. I won't make too many comments of it, but the residuals, check out early office hours. I talked about the residuals on it. But there's the residuals of it. And now that we have to give it the values, because we're kind of doing like a what if scenario, like what if it's a hot day, what if it's a cold day here, we can get the forecast. So it has to have new data to make these forecasts because it needs values of the X's. Hence the problem with making forecasts without it. So now that we have this right here, we've got the forecast. And what we can do with the forecast is we can actually go in here and we should be able to, don't fail me now, we should be able to auto plot it. There's the forecast. But once again, we want to take our original data. And it's Jan Daily Electric. It's not the right data, is it? It's mad about something. Let's go ahead and look. Jan Daily Electric. Oh, we're going to do the book way of doing it, aren't we? Yep, I think we are. So there are the forecasts. That doesn't look so pretty. He does a way of doing this. Let's go to the book again. And grab the data. Here we go, scenario forecast right here. I know he shows it. There we go. There's the scenario forecast, and here it is right here. So he saves the forecast right there. Here's the original data. So it should be this easy. Nice and easy. And because we're doing the forecast, there we go. He's piping the original data, auto plotting it, auto layering it on. So he's auto layering it on afterwards. So we need this to be the January VIC. And then we need to go to the variable we used, which is demand. And there's the forecast. The title is going to be energy demand. And then the Y will be amount demanded. Should like it, and there we go. I think we did a different way during the last office hours, but this is the auto plot of it right here. And one issue I do have is it doesn't let you ggplot this. That's always a bummer to me. But the book has so many great practices with this. But you see your original series right here. We did see this in the time series earlier. So you can look at your time series right there with the dip towards the end. There's the dip. And here's the forecast for hot day, cold day, which really depends if it's going to be a cold day. We also talked about the issue with the colors during the last office hours. You would have to recode this to be like 0 hot day or something. And then you will see hot day has the red now, which makes a little bit more sense. But maybe you could do something like freezing day, A, B, C, D, F, G. No. Let's say freezing day and A, B, C, D, E, F, G, H, I. I can't think of a boiling day. That's what I wrote last time. Boiling day. Makes more sense like here if you write boiling day and a freezing day. Yeah, so the way it does the color coding is based on alphabetical. There's probably some other way with like scale, color, manual, fill, or something to change it. But if you just kind of work within the bounds of the system, that's the way it does it right there. I mean, if the grader were to take out points for changing the names of them, I would say, what are you doing? I think it better communicates the idea if the colors red and blue, which we kind of consider with hot and cold, make more sense on this. And these are the things you might want to consider if you're doing things graphically, because people might look at it and think this is the hot day, which it is now. There's probably a way to do it outside of that. I do always get mad about this though, because we'll store our graphic into P right here, and then we'll go ggplotly of it. And I hate this. If you do this, it won't show up with the things. For some reason, it's not coded. It says like has not been implemented yet, so you can't use it. Unfortunately, it would look really cool in this, but you can't. So one of these days, maybe they'll add that over to Plotly, but unfortunately, it can't be ggplotlead. Abigail Carter, does that make sense? Sorry, my brain overheated. And thank you, Abigail. 100 points again. Definitely at the start of that, my brain was just like, wait a minute. Filter. I couldn't even get the filter going. What's wrong with me? But yeah, sometimes your brain's just like, what am I doing with this code? I tell people it's funny. And sometimes the coding's easy some days, but the interpretation is really here what matters. No, you're welcome, Abigail. Thank you for being here. Thank you for the practice. It's the end of the week. All of our brains are overheating a little bit. I love all the positivity because every time everyone gets stuck a little bit, I just do it for fun. It's that time of the week. It's the Haslam Friday. Great work right there, Abigail and Carter. And thank you both so much. And we're going to throw you both 1,000 points. No one else watching 1,000 points. I like that positivity. Meanest thing a student ever said to me was, do you even know how to solve this? When I get something wrong or I can't get something right, I get anxiety. You might say, Brian, you get anxiety? I say, everyone gets anxiety, I bet. So, yeah, it's just sometimes if you just can't think about it, your brain just goes in circles and spins. And you're like that loading screen or something. And then you're just stuck. And Abigail, you were great right there. A huge help. So every once in a while, your brain just goes, nope. It's like Homer Simpson goes, if you've ever seen the old Simpsons episodes. All right, so let's do the train and t-shirt question. These will be pretty quick. I might do shorter versions of these. And then, John, we'll be on to your question. John, thank you so much. That was Q1A too. So we'll take Q1A off the list because we just did some Q1A right there. So that was Q1A also. You're welcome, Abigail and Carter and John. So, John, hang tight. We'll be here in a moment doing some 320, and then we'll have 320 class. We're doing the train question in just a second, but a student afraid that they're going to miss the train. Let's find out if they missed the train. Okay. Ooh, got some good numbers right here. Okay. So, wait, don't have the thing ready. Train question coming right up. Here we go. Time for the train question. Here we go. It's time for, you called it, Hackerman. Hackerman looks at it and says, 10% chance of being late if he's late out of class, 3% chance of missing the train. Done. Hackerman solved. Should we go to the next question? Oh, let's talk about this. Question solved. How do we solve this? What does it mean? I got some lucky on the numbers is what I got. Okay, so this question right here is a contingent probability. It's using the multiplication rule, and sometimes people are a little bit confused. Why does it work this way? Well, it says the student has a 10% chance of being late out of class. Like, if we write this down, then probability of late is equal to 10%. Probability of not late is the complement of it, because he's either late or not late. It is a he today. Right here of 90%. Now, if they are late out of class, they have a 50% probability of missing the train. And that's only if they are late out of class. They have a 50% probability of missing the train. And so that would happen 50% of the time if they are late out of class. Now, that means they will catch the train. So the C there stands for catch 50% of the time. So if you see, I got very lucky on the probabilities because what we're asking about is the kind of event that they are late out of class and then they miss the train. Now, you might say, well, wouldn't them missing the train depend on them being late? That is true. The probabilities actually change down here on the bottom if we look at a full solve of this problem, where if they're not late, the problem doesn't tell you this, the probability they miss the train would actually be 0. They're not going to miss the train if they're not late out of class. The probability they would catch the train would be 100%. If they are not late out of class. The only scenario that this problem cares about here is going to be the scenario in which they are late and then they miss the train. If you actually solve through for all the probabilities, you would see the probabilities up top are going to be probability of late and missed train is equal to 5% of the time. Probability of late and catch train is 5%. Probability of late, and remember we're saying and right here, probability of not late and missed train is equal to 0. That just can't occur because if they're not late, they will always catch the train. And what's really great about this is if you notice, we can use the addition rule right here, and the set of all probabilities would have a sum of 1. And the only answer we're looking for is the 5% right here. But listing this out as everything that could occur, they're either going to be late and miss the train, they're going to be late and catch the train. There is the idea of them being not late and missing the train, but that just can't occur because if they're not late, and the problem doesn't say this, but it's implied that they wouldn't miss the train. So it is true that these are dependent, but it does give you the probability up here. So these are dependent, but we do know the associated probabilities with the dependency. I've never seen a test question that quite asks it this way, but test question could list something out like, if this occurs, then this has this probability. Maybe I have seen some. So it could say, if somebody is late, they have a 50% chance of missing their train. And then the probability of them being late and missing the train, because it's saying, if this occurs, then this has this probability. So it's like a sequence, like, okay, 10% of the time this would occur, and then it's like a subset within it, then you would only say 50% of the time, so it'd be half of the 10%. Good question, good practice. Maybe I've seen a test question that goes that way. Maybe. I don't know. I just can't remember. Back to the main screen for one more probability, then some 320. Okay, one more probability question with the t-shirts, I believe. Let's check out the t-shirt question. Playing 2 songs. We did the train question right there. Hey, Madeline, good to see you here. Let me know if you have a question. We have just enough more time to do a few more. We're going to do the t-shirt question here. Going to get back our black t-shirt, as Ben Folds would say. He was writing songs, Mr. Ben Folds. The t-shirt question. Let me know if you have questions in the chat. Here we are with the t-shirt question. Going to re-timestamp it. Let's go check it out. Do you have time for one? Ask away. We'll try to do it. Ask questions. We try to do them as much as we can. Thacker, thank you for being here. Let's throw 100 points out to the chat. So this is the t-shirt question. We have, what is the probability of a random t-shirt being red or not black? Oh, not a black t-shirt today. And so we need to draw this out. Let's take the table and draw out what we have. Here is our dresser drawer. 2D, 475. Take a look at some 2D. And so here's our t-shirt drawer. We have red, black, and blue t-shirts. That's all we own. So we have 4 blue t-shirts. Those are t-shirts. Impeccable drawing here. We have 9 red t-shirts. And then we have 3 blue shirts. 4 black t-shirts. Why do we need our black t-shirt back? We have 4. We got extras to spare. They have all the black t-shirts. So now we're asking, what is the probability a random shirt is blue? Well, it's kind of likely. We're just going to take all these and throw them into the drawer together. It's kind of likely that we would just randomly pick out a red t-shirt when we grab into these t-shirts right here. But we have to think about how many t-shirts there are total. And the total amount of t-shirts are going to be that there are 16 t-shirts. That's a nice number. This is the formula X over N right here to tell us the probability of something. There are 16 total observations, and then we want to know how many red t-shirts there are. There are a total of 9 red t-shirts. That would be 56.25, I do believe. 9 divided by 16, 56.25. That is correct. 56.25. And then we want a not black shirt. Well, not black is the complement of black. So what is the probability of black? Black is going to be 4 black t-shirts, a nice number, which is 1/4. So the probability of a black shirt is 1/4. The complement is everything but, which is 3/4. It basically is the remaining probability. So it's either black or not black. And the probability of not black is 3/4. And that should be the answer here. 3/4 is 75%. 3/4 right there, and check answer, and we've done it. Back to the main screen. We got some 320, then we'll try to do 2D. Did we do? Might have did a little. What is 2D? Let me look at 2D. Did we do any 2D today? We didn't do the high-low intervals. Okay, that's the high-low. So pipe it through the high-low. Yeah, I'll take a look at that here. So we got 320. 320 time. 320 question. Let me put 2D on here before we forget. 2D. And 321G. What's up, Decker? 1G. A, B, C, D, E, F. I think I get that coffee crash. Like, I got all that energy, as BTS once said in a song. And then I start to lose that energy. It's just... It's Hasm Friday. So much fun. Reported 95... Ooh, we got confidence intervals for 320 here. Reported 95% confidence interval for the coefficient of effective temperature. Explain what this means, as well as the p-value implies the effective is not... Okay, cool. Okay, let's take a look at 1G and take a look at confidence intervals for regression models. Okay, got it up. Okay, so the timestamp on this is going to be 112, 4 to 3, 4 to 3. Let's take a look. Here we go. So we're going to make a confidence interval for coefficients in regression models. Let's say not your code again. Do not use the code I'm doing right here. This is not your code. So it's just a disclaimer right there to make sure you don't do the same thing I do. Don't do this. Don't do the exact same thing I'm doing. We need to make a confidence interval for the regression model. Why is the code looking like this? Why is it looking all crazy? Let's make a regression model right here. And I'm just going to make from... Do I still have Survey 10 loaded up? I don't think I do. Survey 10, best survey ever. 2010, amazing year. And we're going to make a regression model from the following. Let's use height plus GPA plus desired weight. Data equals survey 10. Hey, that worked. So our model has those variables in it. We don't need the summary here. Let's put not needed. And so now let's take a look. There's only one variable here that is not statistically significant. So John just got back from the dog park and I saw, yeah, of course. So there's only one variable here that's not statistically significant. What variable is not statistically significant in the model? Question for 2A, the forecast portion, does it matter? Telemarketer. Probably not. I don't think so. And GPA is not, so I don't think so, Carter. Maybe double check with me. It's weekly data, so yeah, you could do that. You could do that. Plot the next year data. That's a good answer, Carter. 100 points right there. I'd plot maybe the next year. That sounds about right. Weekly data, so horizon of 52 years, and that's what the H stand. Always try to know what your arguments and your code stand for. Anytime I'm confused on a code, it's usually because I don't know exactly every argument. So H stands for horizon, which is your forecast horizon. So you're just saying, how far am I forecasting into the future? The horizon. Bring me that horizon. And this is not statistically significant. So we're going to go and look at the coefficients intervals. And I can already tell you, John, you might be able to already tell me that this is going to be the interval we're about to see. But it'll be, well, okay, we'll do it real. This is the interval we're going to see right here on the screen, John, when we look at the confidence interval for the coefficients in this model. And remember, I just did a quick estimate. And how in the world did I do this, John? Good review of our concepts. Why was I able to say it's going to be about 0.5 to about -3, -3.5? Now, it wasn't exact because I maybe should have added on another decimal right there. So in truth, I'm just doing what basically? It was close to 1. So I said, it's about 1. That's about 1.5 and that's about 1. So I just went out 2 whats. And you'll see a very important thing about this interval right here. And then we'll interpret it, we'll make sense of it. So we're trying to think, what is the true coefficient of GPA in this model? Does that make sense? Like, what is the true coefficient? Like, how much does GPA actually impact somebody's weight? What is the truth? Exactly. And we're going on 2 standard errors. It does it for us. We don't have to do this ourselves, but we should understand conceptually, and we literally just saw this today. Literally here, I was going to say literally like 10 times, we did confidence intervals today in our class in 475, and look right here. Same concepts. The same concepts of confidence intervals and making predictions are the same exact thing, and I was drawing this out for 475. So the idea of confidence intervals being basically 2 standard deviations does not go away. So or standard errors, standard deviations, depending on how we're talking about the model. So we are doing that right here by creating an estimate for the true coefficient of a variable in the model. This is not a prediction interval like we just saw on the screen. This is a confidence interval to estimate what is the true impact of GPA. And I would say I am 95% confident the true coefficient of GPA is contained in the interval negative 3.6, whatever, to, and I just copy paste that number, 0.58. Does that make sense? I am 95% confident the true coefficient of GPA is contained in the interval blank to blank. How are you following me with that, John? Like, I am 95% confident the true coefficient, like the real impact of GPA, that what it actually does when predicting weight, like the truth, if I could know it, would be contained in this interval. I don't know what the truth is, but I think it could be somewhere in this interval. Yeah, it's probably about between here and here, maybe. But the thing about this interval that's very important is that the interval contains inside of it 0. 0 is the naive model. 0 means that the thing could have no impact. Like, maybe, makes sense. Exactly. We're just saying, I think the true coefficient with 95% confidence would be contained in the interval blank to blank. And then because 0 is inside of here, it's like, well, maybe it doesn't have any impact. And if it doesn't have any impact, it's not statistically significant. You'll notice these intervals right here are going to be statistically significant because they do not contain 0. And also we can see the concept again that 2 standard errors right here is times 2, which basically goes from -2 to -1 because you're just doing 2 standard errors. Very important stuff to know. This is the most statistically significant by the t and by the p-value. That is the most statistically significant. I've asked questions like that before because the higher the t in absolute value, the lower the p-value. So I have thrown a question on the test before, John, like which variable is the most significant? And then I've shown things with multiple things that have like 2e to the -16, and you'd have to look at the t-score. So you'd have to know like larger absolute value of t means more statistically significant. Like smaller absolute value of t is less statistically significant. Larger absolute value of t means more statistically significant. So, and you can see the tiny little uncertainty. Like this is a similar estimate. So even though this has a bigger estimate, this actually has the biggest estimate in terms of absolute value, but has the most uncertainty. This has the smallest absolute value estimate, but has the least uncertainty, which kind of makes sense. Someone's desired weight probably explains decently what they weigh. Not saying exactly, but that's where a lot of the explanation and variance is coming from. Variation explained is. We missed someone's weight by 100. We missed someone's weight by negative. Wow, that's a lot. We got just enough time here to do a little more 474. Let's go back to the main screen. I've gone. Maybe Fleming, drop it in the chat. Ask away, ask away. We're finishing up. I'm gonna send out the announcement to 320 to remind them to come to class right here. We might do some speed running of questions. Thank you everyone for being here on Haslam Friday. Throw out another 100 points. Drop those questions in the chat at any point. Say, hey Brian, I'm working on this question. Can you help out? And I will do my best. We might speed run questions at the end. With the time we have, we will try and make the best of it. We are on to the last 10 or so minutes. Class in 20 minutes. See you soon. I have forgotten to send out a class in such and such time. And then, like, so few people show up. Oh, it's so bad. It's so sad. I just, like, I'm like, no, if I don't send that out, people don't show up. Sad times. Q2D. A student figures figured it. So we actually just did that one at the 1 hour mark. So check it out, Fleming. We might not have enough time to go back to it. Don't drop it in the chat. But I'll start looking at it here. So Fleming, if I don't have enough time, we did that one in the morning office hours. And we did it today. We did it. Catch Train starts morning office hours, and we just did it about 10 minutes ago. Yeah, so check it out. You're welcome. And it's in the morning office hours too. So if you want to see 2 solves of it, morning office hours I did in 7 minutes. Afternoon office hours I did in 4 minutes. We speed ran it earlier. So Fleming, great work. 100 points, Fleming. Thank you for asking. Oh, I love those cat box emojis. Share message me on Discord. I'll take a look here. We'll talk about it. I might solve most of the code anyways. Let's take a look. Final 10 minutes. So yeah, you can actually rewind this video live. I think a lot of people know that you can actually just scroll back on the video and rewind time. Let me get the assignment up here. 1 second, Thacker. Okay, there we go. Okay, let's go check this out. Here we are on question 2D. Or not 2D. 121. There we go. Here we go. And let's take a look at it. So in this question, we have to have our previous, and we've already been doing a little bit of this, we have to have our data already made, our predictions already in here, and we want to create some intervals. Now, Adam Spanbauer, absolute legend, has created this function for us that is going to take and kind of make sure this is included in our output. He mentioned that sometimes people aren't including things in their knitted document because I think sometimes we just knit it and don't look at it. Not good, not good, not good. So he has it where it's going to output this table right here. Great code, great practice, excellent job. And so with this, he should send that to Rob Hindman because that's much better. Like, hey, this doesn't knit. So here I created something that makes it knit. Amazing work. With this right here, we need the intervals for these predictions. And we're doing D, right? Where's the, here it is. Give prediction intervals for the forecast of the next day, which we already did that. Here's the next day. And we were plotting it just a second ago. Check out the earlier plot. We confirmed you can't ggplot it, so don't ggplot it. And here's the forecast. We also changed the names of it so we could get the color coding more accurate to boiling day and freezing day. And now it looks more accurate to the color coding. So that's why we changed the names of them. You can change the names too if you want. The main thing we want to know right here is that our forecast is saved into here. There's our forecast. And let's go ahead and grab these forecasts right here and move forward with them. Give prediction intervals for your forecast of the next day, and we want to grab these intervals. You can see the intervals right here and kind of understand what you're looking for. The freezing day should be down here at about, what's that, 100,000, and should go up to about 200,000. The other day, and that's for the 95%, the other day will be even higher for the boiling day. So it's got all this good stuff right here. Your code, I think that we should be able to take this, your code 2. So we need to pipe through our model. And we should be able to just take our model, take the fit. There's the forecast. Let me double check. High, low, explain high, low. We should, I think the forecast can just be put through there. Pretty sure. Put the forecast through here. There we go. And, oh, didn't close it. Didn't close it. There we go. There's that. Hey, what's up, Madison? Good to see you here. This is, 1D? Adam is the GOAT. Adam is great. Are you talking about 1D? And so what else do we need at the end of this? Because this should be your interval right here. If you take a look at this full interval right here, 1D, sibling office hours go, I'm going to throw some 500 points for sibling office hours right here. I love it. Good stuff right there. Good sibling office hours. There we go. There's the intervals, and that's what we're seeing on the screen right here. Was it 1D? I thought it was 2D. Sorry about that. I marked down 2D. No. We'll look at some 1D real quick. Oh, the Legendre box test? Oh, I was like, this didn't look like the Legendre box. Oh, sorry about that. Let me go grab that right there, Thacker. You were asking about the Legendre box test. Let's go look at the Legendre box test. So when we do the Legendre box test, we actually need a model, and we need to know how many parameters in that model. So I'm going to make a very, very simple model right here. So, oh, no worries, no worries. One thing that's really great about this, and we're just let me do a quick segment right here. Okay, so let's go do, well, that was 2D. It was a very quick segment on 2D. Let's go do 1D, and we'll timestamp this here. And let's go do a little 2D right here. 1D. So with 1D right here, 1D is going to be the Legendre box test, which we talked about today during class. So definitely check out class today where we're going through. That's still 2D. 1D on the Legendre box. Am I losing my mind, everybody? Did I do it in the place of 1D? Are you talking about, oh, I did 1D. You want 2D. That was 1D. Oh my gosh. So I did 1D. You want 2D. That's what it is. Okay, cool. Okay. So we need a model right here. What is the Legendre box test? This is going to be a test to see if there's significant autocorrelation at a certain lag. I'm going to make a very simple model right here, and I'm just going to run some data through it. This is not quite your model. So let me go here to the OS production data. We're going to grab some OS production data. Let's do this. Let's make a model right here. Let's go in here and select. Let's select electricity. There we go. There's the electricity demand right there. Let's take the column we've selected right here and go to model. And let's go to the naive is equal to, it's going to be, man, if we do that, say naive equals naive. And the naive doesn't take anything. There we go. There's the naive model. I think we're good on that. We'll think we're good. Let's look at the GG time series residuals. Should like it. Here we go. That's, oh my gosh. Wow. I can already tell you the value of the Legendre box test by looking at this. And what am I looking at? The Legendre box test, and we'll bring up the notes right here, is going to show us the amount of, if we have significant autocorrelation up to a certain lag. We'll look at one more thing right here. Let me look at the glance. And the naive model has really bad. It's not even giving us extra things. The naive model has no variables in it. So it has no parameter estimates. The naive model is going to be the baseline starting point. And let's go ahead and add on. Now this one, I always have to look up the code for the Legendre box. It's using the features. So let me go grab the code for it. Oh, we have it in the notes from today. Let's go over to it. Forecast, decomp, evaluating, residual diagnostics. Based on the visual, would you fail to reject the null? No, we would reject. Based on it's going to be a low p-value. The p-value on this is going to be ridiculous. The p-value here will be horrible, horrible, horrible. So we have to augment. There it is. The p-value on this is going to be ridiculously bad, and we'll see that very quickly. So let's put a fit right here. These residuals are very bad. These are very bad residuals because there is an increased heteroscedastic relationship. Oh, no worries. And let's go ahead and augment this fit right here. There we go. There's that. And now we're good on that. You have to take the augmented fit. And there it is right there. Augmented fit, pipe it through into the feature. Make our code look nice. Using the baseline, no augment. There we go. Wow. As I said, p-value of 0. What we're mainly looking at right here is the following. There is significant autocorrelation all throughout this. The p-value right here, we're looking to lag 10, which is just very evident. Definitely check out today's lecture where we go into more detail on this. So if you're wanting more detail today during lecture, and I marked it, it is we go into a lot of details at the very start here. The Legendre box test, we spent a good 6 minutes kind of going over the output and when you would see a low p-value or high p-value. So is it standard to use the lag of 10, the degrees of freedom 0? The degrees of freedom 0 are based on the parameter estimates. Definitely check out today's office hours. We set it to 0 for a model with the raw data. The naive model is not really using any parameter estimates, so I set it to 0 right there. But if you have a Fourier model, I would look at the parameter estimates in the model. So the degrees of freedom are the parameter estimates. Lag of 10 is probably okay. You could go to 20, but when you have larger sample sizes, it's going to cause problems. Definitely check out today's class. If you don't have access to it, let me know. But I go over this more in depth on today's class, talking about the significant autocorrelation and when we would have evidence. This is actually a good thing. A low p-value here is bad low p-value. We don't want that. We want to see a high p-value here because this is like 320 when we want to see high p-values for assumptions. And if we see a low p-value, it means there's significant correlation at some point through a certain lag amount. And it's quite evident. Awesome. Good stuff. And you will see right here, there is significant autocorrelation. This is ridiculous. There is, and this is quarterly, so there's a yearly pattern, it looks like. But that's got it. Let's head out. We'll head out. I will see everyone later. Great work. Hasm Friday. Bye for now. Bye, everybody.